All right. So Tuesday, I posted the first assignment, so I want to make sure we're all on the same page with that. Did everybody see it? Okay. Anybody have trouble finding it or finding the associated problem? So on the announcements, it listed a bunch of problems. Anybody have trouble finding what problems I was referring to or anything like that? Okay. Well, I just want to, so it's only been the one time, but I just want to reiterate that those problems are, even though you're not turning them in directly, doing those problems is like the heart of this class. So you need to take that stuff seriously. If you get a class behind or whatever, you have other stuff to do, that's not really a big deal, but you want to try to stay on top of it as much as you can. And I also want to remind you that, so there are solutions for all of these problems available, but that can be kind of a, that can sort of sucker you into trouble if you're not careful. You don't want to get in the habit of looking at the problem and then quickly just going and looking at the solutions to see how to do it. You need to try to do the problems without the solutions. Use them as just as a little hint if you get stuck, or after you're done to compare your work to the. Okay. Yes. Oh, well, that's no good. Let's see. Other people think that too? Okay, I have them. Okay, I probably took them down so I could update them, and then I forgot to do it or something. Okay, I'll get that up. Thank you. Any other questions? All right. So, like pretty much every semester, the first test comes or whatever, and somebody comes and talks to me and they're not happy with their score, and then they're like, yeah, I did like some of those problems, but like really those problems are what this class is about. 75% of the grade is exams, and the exams are so close to those problems. You really want to be comfortable with those, okay? All right. So last time we finished talking about units and scientific notation and stuff. In a way, today we're getting into the first topic that's actual physics. So today we're starting kinematics of a particle in one dimension, or 1D kinematics of particles. And so let's talk about what that means. 1D means along a known path. Where at any location, there are only two directions. No. Two directions. Okay, so in the world we live in, that's not true. So if I'm here, I can decide to go to the door, or ram into this table, or if I flap my arms hard, I can go up. So I have, at any instant, I have more than two choices of where to go. But in one dimension, like along a line is going to be the most common case for us. You have two choices. You can go forward or you can go backwards. Mostly we're going to do things that involve moving along a line, but it doesn't have to be along a line. And then kinematics means that we're describing motions without considering the causes of motion. This will be mostly relationships between position, velocity, acceleration, and time. And then the last thing is particles. And particles are just treating objects in a way where we lose any orientation information. So we're concerned with location but not orientation. Okay, so since we're going to be dealing with particles for almost the whole class until right towards the end, I just want to be clear about what I'm talking about there. So we will deal with things like circular motion, and when we deal with circular motion, we're going to be able to differentiate between, like all of these, we can talk about motions like this, okay? Like I'm going in a circle or whatever, going over here, going back. We can deal with that. What we won't be able to deal with is this. If we're treating me like a particle, then I'm not doing anything. I'm staying in place. You know what I mean? That's changing orientation, and that's the information that we lose when we're talking about particles. Okay, so with particle kinematics, we're dealing with relationships between position, velocity, acceleration, and time. So let's think about what it means to put a numeric value on the position of something. So we'll start with talking about position. And so let's say that those are train tracks, because I'm good at drawing trains, old-timey trains. See how good? Thanks. Okay, so what's the position of that train? That question doesn't mean anything yet because we don't have anything to reference it to. Even if we say like, okay, we know what a meter is or a foot is or whatever, like how many feet is the position of that train? You know what I mean? It doesn't make any sense until we have some kind of reference. That's true in everyday language too, like if you say, where is 7-Eleven? You say, well, from here you go out a block and turn right and then whatever, but you don't just say, you can't just say 40 or whatever. That doesn't mean anything. So in order to define position as a number, what we have to choose first is something that we're going to call position 0. That's our reference. So to define the position, we need to first choose a 0 position. And in this case, I guess I'll say, I'm going to call this the 0 position. Okay. So that means we have to choose a physical thing that we're going to say is at position 0. And now can we put a number on the position? Not exactly. We're a lot closer than we were before. You could measure the distance from 0 to here, say that's 20 meters or something, okay? And so maybe you could say the position 0, but notice that even in one dimension, saying that you could say, say the position's 20 because it's 20 meters away, okay? Even that, it doesn't give a unique location there because there's also a point over here that's 20 meters away from 0, okay? So we need to do one more thing. We need to decide which, at any point in one dimension, there's only 2 directions you can go. We need to decide which one of those we're going to call positive and which one we're going to call negative. So if we choose a 0 position and a positive direction, now we can say, okay, so let's say this is what we're going to call positive. Then the position has an absolute value of the distance from the 0 that chosen 0 point, and it has the sign of the direction that you have to go from 0. Okay, so if this distance is 20 meters, and with a particle, you always have to represent it by a single point. So I'm going to choose that red point, the center of mass. And let's say that this distance is 20 meters. Then what's the position of the train at that point? Yeah, so it has, the absolute value is 20 because that's how far it is from 0. And you don't get there by starting at 0 and going in the positive direction, you go in the negative direction. So in the example above, the train's position and we're going to represent position with a lowercase p, is equal to negative 20 meters. Okay. We're going to usually want to be tracking the position of an object as time changes. So we need a relationship between position and time. We'll want the relationship between position and time. And that means that you have to choose a third thing. And that is you have to choose a 0 time. That's a physical instant when you're going to say time is equal to 0. Basically, the easiest way to think of it is you have to choose the instant that you click on your stopwatch. Okay? And then everything that follows that has a time associated with it, and the thing that you're tracking is at a given position at that instant. As far as units, notice that position has units of length. And that's meters in SI units. And time has units of time. Makes sense. And in SI units, that's seconds. Okay, so I think I'm going to just try going to an example of making sense out of this stuff. So let's say that you have, so on the left of this picture, you have like a little house. And then 15 meters away from that, you have a fire hydrant. And then 10 meters away from that, you have a car. Okay, so this distance is 15 meters. This distance is 10 meters. And let's say that a person walks from the house to the car and then back to the fire hydrant. So the house to the car takes 15 seconds. That's a slow walk. And then back to the car in 10 seconds. Or back to the fire hydrant, I mean, in 10 seconds. And so let's say that we choose, so first, if we choose the 0 position to be at the house, and the positive direction toward the car, or I guess, let me say toward the right of the picture, you know, from the house toward the car. And 0 time to be when the person starts walking. Plot a graph of the position versus time. Okay. So we don't need those elaborate drawings on there. That just sort of confuses things. So there's the house, there's the fire hydrant, there's the car. And we know these distances. Those distances between things don't have to do with any choices that are made about 0 position or anything. So if that's 15 meters, and that's 10 meters. And another thing that doesn't depend at all on our choice of zeros or direction is what the person does. The person doesn't even know we're there. You know, we're like hiding in the bushes filming this person. That's what physicists do. That's most of what physics is. Okay, so the person goes out here and gets to the car, and this leg of the journey takes how long from this point on the left to where the person gets to the car? Yeah, 15 seconds, that's given. And then it takes 10 seconds for the person to get back to here. Okay, so that, none of that is up for debate. That's what happens. We're just now trying to figure out how to put position and time labels on all these different events. Okay, so now for the first time, we're going to take into consideration the zero position, the positive direction, and the zero time. What did I say was the place that we're going to call zero position? The house, yep. So this is whenever the person is here, they're at location 0, position 0. Okay. And what did we say was the positive direction? Toward the car. Yep. So positive goes this way. And now that we have those two things, we can put numbers, numeric position values on all the things, the important events that happen. So if you start at 0 and go 15 meters in the positive direction, what's the position at that location? 15. Oh, just let's go point to point to point. So at the hydrant, you've gone 15 meters in the positive direction. So this is at the position whenever the person is at the hydrant is positive 15 meters. And then the car is another 10 meters in the positive direction. So what's that? 25, yep. And now we know the elapsed time between these events, but now we can put time labels on all the places where I've drawn these points. I said 0 time is when the person starts walking. So we'll label this 0 seconds. Okay, that's when you turn the stopwatch on. And then the next thing we know is when the person gets all the way to the car. That's at 15 seconds. Because if you start at 0 time and then 15 seconds go by, your stopwatch says 15 seconds. And then another 10 seconds later, you're at 25 seconds. And so I'm going to put this, I think for stuff like this, at least at first, this is helpful to do. I'm going to just write out a little table of corresponding times and positions at the instance that we know about. So here are going to be the time values, here are going to be the position values. So the first thing we know is when the person starts walking, the time is 0 and the position is 0. We don't know anything about what happens when the person goes by the fire hydrant, so we don't know anything else until we get all the way to the car. But when we get to the car, we know the time is 15 seconds. And we know the position is 25 meters. And then the last thing we know is that when the time is 25 seconds, the position is, what's the position there, that last instant? Back to 15, that's right. And now we have these 3 points that we can plot on a graph. If you make time your horizontal axis and position your vertical axis, the important times are 0, 15 seconds, and 25 seconds. And the important positions are 0, 15 meters, and 25 meters. And now I'm just going to read these values off of my table. The first one is 0 time, 0 position. So graphing that point is here. The second time is at the second instant that we care about is at 15 seconds. And the position is 25 meters. So that's here. And then the third one is at 25 seconds and 15 meters. So here. And if we knew more details, if we were given 100 locations, we know they were at the flower before the fire hydrant at 13.2 seconds. The more details we knew, the more detail we could put in this graph. But based on what we know, as far as we know, it's just basically like this. Okay, so this graph tells us whatever time you want to know, like say you want to, I mean, I guess in this case, we're just sort of guessing what happens between these points. But say you want to know where the person would be at 10 seconds. Go on this graph to 10 seconds, go up to the position, and you're like, okay, somewhere around the, somewhere around the fire hydrant. This position versus time graph shows position as a function of time. And so now you can sort of maybe start to imagine how we're connecting up physical things that happen with mathematical things. I could, like, for example, give you the mathematical function that represents these lines, and then you can use that function to figure out where the person is going to be at different times. Okay, and whatever things you can do with functions, you can now do relating the position of the person and the time that it happened. Well, what would that be? That shouldn't be too hard. So like, for example, this line right here, that's the easier one of the two, is the function t as a function of time is equal to 5/3 t. And so if you plug in any t value into that function, it tells you what the person's position is. That's the basic idea of what we're going to be doing with kinematics. Oh, and we're also going to be dealing with velocity and acceleration. All right, let's do the same problem, because I know no one ever gets tired of doing the same problem over and over again. But this time, so it's going to be the same motion. We're still, so let's imagine now, so we're in the bushes filming this person. There's another physicist in a different set of bushes watching the same thing happen, okay? But we're not in communication with them. And that person makes different choices of the zero position, positive direction, and zero time, okay? And so let's do the same exercise again with just different choices of those things. The motion's the same, but we'll see what changes about the numbers, okay? So let's do the same question. Or the same motion, I guess is better. But this time, let's choose the zero position at the fire hydrant. And the positive direction to the left. And the zero time, let's say that this other physicist clicked the stopwatch on 5 seconds before the person walked out the door, okay? So zero time, 5 seconds before the person starts walking. Okay, so I'm going to draw this little representation, the same as I did in the first case. And remember that there was a lot of stuff on here that didn't have anything to do with our choices. No matter what we choose, the house and the fire hydrant are 15 meters apart. And the fire hydrant and the car are 10 meters apart. And no matter what we choose, the person starts at the house. It takes 15 seconds to get to the car, and then takes another 10 seconds to get back to the fire hydrant. Okay, so now we're going to use the new choices, excuse me, to label the times on these instants and to label the positions at these physical spots. So where's the zero position on this one? Yeah, so whenever the person is at the fire hydrant, that's the person's position is zero. And which way is positive? Yeah, this time positive is to the left. And so now we can label these two other important spots. If you start at zero and go 15 meters in the positive direction, what's the position at this point at the house? Positive 15. And if you start at zero and go 10 meters in the negative direction, what's the position there? Negative 10, yep. And then we said that this physicist clicks the stopwatch on 5 seconds before this instant. So what does the stopwatch say when the person starts walking? 5, yep. So this is 5 seconds. And then it takes 15 seconds from there to get to the car. So what does the stopwatch say at that instant? 20 seconds. And then it takes another 10 seconds to get here. So this says 30 seconds. Okay? And I'm going to write out this little table again. The 3 instants that we know about. The first one, the time is 5 seconds. And the position is 15 meters. The second one is 20 seconds, and the position is -10 meters. And the third one is 30 seconds, and the position is 0. And now to plot this, the times that matter are 0, well, 0 doesn't come up, 5 seconds, 20 seconds, and 30 seconds. And the important positions are 0, 15 meters, and -10 meters. And now to plot this, we can just read off the graph again. So at time 5 seconds, we're at 15 meters. At time 20 seconds, we're at -10. And at time 30 seconds, we're at 0. And so the graph looks something like this. So notice that your choices of 0 position, positive direction, and 0 time can, so changing the 0 position shifts the graph up and down. Changing the 0 time shifts the graph left and right. And changing the positive direction flips the graph. So the idea is there's nothing, well, I shouldn't say there's nothing, but these graphs are not, and these functions that go along with the graphs are not universal descriptions of the motion. They're always going to depend on your 3 choices of things, okay? And as we go through, like once we get to real problems and stuff, I think it's a good idea to be very clear to yourself always about what those 3 choices were that you made, okay? I'm going to do that when I do example problems, and I think you should at first too. Later on, once you've done a lot of problems, you might not feel like it's necessary anymore, and that's fine. But I would start by being really clear about that. Okay, let me give another example, and you can work on it together with the people next to you, ask each other, compare answers, ask me if you get stuck. All right, so let's say that there's a pendulum. And it starts out over here, and it swings from there across to the left. And let's say that it swings 0.1 meters to the bottom in 1 second. The next 0.1 meter to the left takes another 1 second. And then the next 0.1 meter to the bottom takes another second. So first, let's choose our 0 position at the bottom. Positive direction to the right. And 0 time when the pendulum is released. See if you can draw a position versus time graph for this. Okay, so yeah, you can work on your own, you can work with each other, you can ask me questions, you can come up here, whatever, but just take a few minutes and see if you can make sense out of this process. So I'm going to approach this the same way I did. I'm going to start out with sort of like a little number line that's going to represent the motion. And there are 3 spots that come up in this. They all are a distance of 0.1 meters apart. And the motion starts out over here on the right and goes there to there and then back, and we don't know any more about the motion after it gets down to the middle. But as far as like the legs of this journey, we know that this part takes 1 second, this takes 1 second, and this takes 1 second. And that is all the stuff that doesn't have anything to do with our choices. So now we're going to get into our choices of 0 position, positive direction, and 0 time. We chose our 0 position to be at the middle. And we chose the positive direction to be to the right. So if you start at 0 and go 0.1 meters in the positive direction, what's the position on that point for that point at the right? Yep, that's positive 0.1 meters. Let's see. And if you start at 0 and go 0.1 meters in the negative direction, what's the position at that point? Yep, negative 0.1. And now we have to think about the times at these instants. It said that 0 time was when the thing was released from the right. So This happens at instant 0. And then if you start at instant 0 and go 1 second, you're at instant 1 second for that at the middle. And then another second you get here at 2, and another second you get here at 3. And if I put these in a table, so at that first instant, when it's released from the right, the time is 0. The position is positive 0.1 meter. At the second instant, the time is 1 second. And the position is 0. At the third instant, the time is 2 seconds. And the position is negative 0.1 meters. And at the fourth instant, the time is 3 seconds, and the position is 0. And now graphing that on a position versus time graph is just reading those values. Time is always horizontal, position is always vertical. The times that we care about are 0 time, 1 second, 2 seconds, 3 seconds. And the locations are 0, positive 0.1 meter, negative 0.1 meter. The first instant is at 0 time, position positive 0.1. The second one is at 1 second, position 0. The third one is at 2 seconds, position negative 0.1 meter. And then the fourth one is at 3 seconds, position 0. And if you connect those, this is all the information you're given, although it wouldn't happen, in real life it wouldn't happen, it wouldn't be abrupt like that, it would be sort of curved like a sine or cosine curve. Anybody have any questions about that? Okay. So usually once we get into problems involving velocity and acceleration and stuff, we'll be able to calculate the position as a function of time mathematically. So position will be a mathematical function of time. So for example, we'll see stuff like P of t is equal to t cubed, okay? And if you can graph that function t cubed, then that's the equivalent of what you have up here. What I want you to keep in mind is, so remember that position as a function of time is equivalent to a position versus time graph. So if you know position as a function of time, like we do in this case, you know, this is position as a function of time is time cubed. If you have a function like that, that means that the 0 position positive direction and 0 time have already been chosen. Okay, so if you're just given position as a function of time, it means you don't, those choices have already been made for you. Okay, so if you know position, P of t, then these 3 things have already been chosen. Okay, the next thing we have to talk about, so that was position. The next thing we have to talk about is velocity. And we're going to define velocity in 2 steps. The first one is average velocity. And the second one is instantaneous velocity. And instantaneous velocity is going to be way more important to us in this class. In fact, you know, we're never really going to use average velocity. But the reason we're going to start by defining average velocity is because we need to use that idea, use the idea of average velocity to define instantaneous velocity. So the idea of average velocity is needed to define instantaneous velocity. Okay, so average velocity. For the instant t1 and the later instant t2, the average velocity is the position at the later instant minus the position at the earlier instant divided by the later instant minus the earlier instant. So one thing I want you to notice about this is you need to choose 2 instants for average velocity to be defined. What are the units of position? In SI units, it's meters. Generally, it's just, whatever your length unit is, yeah. And then what are the units of time? Seconds in SI units are just time, right? And so from this, because we saw when we were doing unit conversions, that the math of units works just like the math of algebraic variables. What are the units of average velocity? Yeah, SI units are meters per second because you have, in general, it's just units of length divided by units of time. And that's going to be true of every kind of velocity. So the units for velocity are length over time. And so the SI units are meters per second. Okay, so let's do an example. So let's say that position as a function of time is equal to t cubed. If you graph a position versus time graph, you have 0, 0, 1, 2, 3, 4, 5, 6. So you have 0, 0, you have 1, 1, and then you have 2, 8. So it looks like a parabola, but it's steeper. And the question is, what's the average velocity from time equal 1 second to time equal 3 seconds? I should have, let's do it from 0, sorry. Let's do it from 0 to 2, just so we can look at it on the graph. Okay, so to calculate that, the definition of the average velocity is the position at the later instant minus the position at the earlier instant. This should be 2. So 2 seconds is the later instant. What's the position at 2 seconds? Yep, so we have 8 meters minus what's the position at the earlier instant? 0. And then we're dividing that by 2 seconds minus 0. And so we get a value of 4 meters per second. Okay, so how does that show up on this graph? So this graph represents that position function. If you look at the definition of this, notice that what we have is a change in the y position, the vertical position, divided by a change in the horizontal position. Does that remind you of a mathematical thing? It's slope, yeah. So if you draw a line from the starting instant to the ending instant, the average velocity is the slope of the line from the point T1, P1 to the point T2, P2. So V average is the slope of this line. Questions about that? And what about the sign? So using this formula, could you imagine a case where the average velocity was negative? Yeah, so anytime the later position is more negative than the earlier position, that average velocity is going to be negative. And so what does that sign tell you? This is important. So notice the sign of the average velocity tells you which direction the object has moved from time t1 to time t2. Okay, so I mentioned before that speed, which we're more used to talking about, doesn't have any directional information attached to it. So, like if you're driving 50 miles an hour towards Iowa, your speedometer says the same thing as if you're driving 50 miles an hour towards Nebraska. But velocity is different. Velocity, whether it's positive or negative, tells you the direction that you're moving. It's easy in 1D because you only have those two possible directions. And so we can do it all with positive and negative. When we get to 2D, we're going to have to do it using these things called vectors because you have so many more choices, infinitely many choices of where to go. Okay, anybody have any questions about that? All right, well, let's stop there, and on whatever day, Tuesday, we'll use this idea to define what we really care about, which is instantaneous velocity.